5.5 Understanding linear functions. A linear function is a function that is defined by f of x, and it's normally in slope-intercept form. It's nothing that is an x squared, a square root of something, of an x. It's a function that makes a straight line. So with these linear functions, you have constant rates of change. These constant rates of change are your slopes. So if we look at our first example, it's asking us to create a table of x and y values using the data points from the graph above. So the graph that we were looking at had the order pairs of 1, 210, 2, 420, 3, 630, 4, 840, and 5, 1050. So if we were to make a table with these values, we could have our x values and our y values. So our x values would be 1, 2, 3, 4, and 5. Our y values would be 210, 420, 630, 840, and 1050. Now we're going to use the table to check that the x values have a constant change between them. So if we look at that change, we're going up 1, from 1 to 2, from 2 to 3, we're going up 1, from 3 to 4, we go up 1, and from 4 to 5, we go up 1. So that constant change there is that plus 1. For C, we're seeing that constant if we have a constant change in those y values. So from 210 to 420, we're going up by 210. For 420 to 630, we're going up by 210. From 630 to 840, we're going up by 210. And from 840 to 1050, we're going up by 210. So that constant change there is that it's going up by 210. If we look at D, it says, using the answers from above, what change in x corresponds to what change in y? A change in x of 1 corresponds to the change in y of that 210. So the change in x of 1 corresponds to the change in y of 210. E says all linear functions have behave similarly to the one in this example. Based on this information, a generalization can be made that what change in x will correspond to a what change in y. So a constant change in x corresponds to a constant change in y. And this is where that constant rate of change comes from, or the slope. If we look at the next part, we're proving that linear functions grow by equal differences over equal intervals. So when we do this, we're using a different formula in order to find that constant change happens. So this is just saying that if we look at this proof, x2 minus x1 is going to be equal to x4 minus x3. The slope times x2 minus x1 is going to equal this slope times x4 minus x3. So if we distribute that m in, we're going to have mx2 minus mx1 is equal to mx4 minus mx3. So then if we add in a b to all of these, we're going to have mx2 plus b minus mx1 minus b is equal to mx4 plus b minus mx3 minus b. So from here, we are going to rewrite this using parentheses where that negative comes out to make both statements positive. So that mx2 plus b minus, take that negative out of the mx1 minus b to make it mx1 plus b. We're going to do the same thing on the other side. Factor out that negative. It ends up being mx3 plus b. So this is just saying that f of x2 minus f of x1 is equal to f of x4 minus f of x3. Kind of confusing. We're not really going to be using this, but it does have to do with your linear equations in standard form and point slope form and everything. So if we look at the next examples, we're determining whether the function is linear, and if so, we are graphing the function. Now we can use function tables for this. We can use slope-intercept form. We can find our x and y intercepts and plot the points. It's totally up to you. So what I'm going to do is I'm going to solve each of these for y. For a, we have 5x plus y is equal to 10. So I'm going to move the 5 over by subtracting it and get y is equal to negative 5x plus 10. I know that my y-intercept here is at 10, so that's going to be the ordered pair, 0, 10. And then my slope is at negative 5, so we're going to go down 5 to the right 1. So down 5 to the right 1. So from here, I'm going to have my first point at 0, 10. And then from there, I'm going to go down 5 and to the right 1. Down 5 to the right 1. Down 5 to the right 1. Down 5 to the right 1. So if I plot these points and then I can draw my line through them, I see that it's a linear function. It is a line, so it is linear. If we look at b, we have negative 4x plus y is equal to 11. So I'm again going to solve for y, move the 4 over by adding it, and we get y is equal to 4x plus 11. So if you wanted to use a function table with this, I would do something like negative 4, negative 2, 0, 2, and 4. We have y is equal to 4x plus 11, and we're solving for y. So if we use the negative 4, we're going to have 4 times negative 4, which is negative 16, plus 11. That's going to give us negative 5. Then we have 4 times negative 2, which is negative 8, plus 11, which is positive 3. Then 4 times 0 plus 11, that's 11. And 4 times positive 2, which is 8, plus 11, is 19. Then we have 4 times 4, which is 16, plus 11 is 27. So if we go to plot these points on our graph, we have negative 4, negative 5, which is here. Then we have negative 2, 3, which is here. Then we have 0, 11, which is here. So we have a line with these points. This is linear. If we look at C, we have 6x plus y is equal to 12, so we're going to do the same thing. This is in standard form, so it's automatically linear. If that 6 is positive and that 6 is positive and your x comes first, you don't have any exponents, you don't have any square roots, then you have a linear function. So automatically, dead giveaway, it's in standard form, it's a linear function. If you wanted to solve it for y, we can subtract the 6x from each side and we have y is equal to negative 6x plus 12. So this is telling us that our slope-intercept is the point 0, 12, and then our y-intercept is the point 0, 12, and then our slope is negative 6. So this means we're going to go down 6 to the right 1. So we're going to plot the first point at 0, 12. Then we're going to go down 6 to the right 1. 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 So that gives us those points that we need. And we see that this is linear as well. If we look at our next set of examples, we're modeling with linear functions. So we're given a word problem, and we're to come up with that function and find out what type of graph this is. We have two types of graphs. We have discrete graphs and we have continuous graphs. Discrete graphs are just points on a function or a coordinate plane. Your continuous functions are lines on a coordinate plane. So with this first example, we have Sal opens a new video store and pays the film studios $2 for each DVD he buys from them. The amount Sal pays is given by f of x is equal to 2 times x, where the number of DVDs where x is the number of DVDs purchased. So this here is a dead giveaway that this is a discrete graph because it's $2 for each DVD. He's not going to be partial. It's not going to be part of $2 for any part of a DVD. It's $2 per DVD. So this here is is a discrete function. If we take f of x is equal to 2x and we form a function table to find our x and y's, he can either buy 0 DVDs, 1, 2, 3, 4, and so on. So we're going to have 2 times 0, which is 0, 2 times 1, which is 2, 2 times 2, which is 4, 2 times 3, which is 6, and 2 times 4, which is 8. And this would continue to go. So our domain here would be the value 0, 1, 2, 3, 4, and so on. The real numbers 0, 1, 2, 3, and so on. Your range would be 0, 2, 4, 6, 8, and so on. If we went to plot these points on our coordinate plane, it would be 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, and then we could actually keep going to where we had 5, 10, and 6, 12 as well. If we look at B, it says that Elsa rents a booth in her grandfather's mall to open an ice cream stand. She pays $1 to her grandfather for each hour of operation. The amount Elsa pays each hour is given by f of x, where x is the number of hours her booth is open. So because she can be open for part of an hour, this would be a continuous graph because it's not a specific 1 hour, 2 hour, 3 hours. There's time in between those hours. So it could be continuous, or it is continuous. If we use the function f of x is equal to x to find values of when her shop is open, she can be open for 0 hours, 1 hour, 2 hours, 3 hours. She can be open for 3.5 hours, so on. So this is going to be f of x is equal to x, so we're going to have 0, 1, 2, 3, 3.5. So our y values are going to be 0, 1, 2, 3, and 3.5. This is telling us that our domain is the set of all numbers greater than or equal to 0. So our x values are going to be greater than or equal to 0. Our range is the same thing, but for our y values. So it's anything greater than or equal to 0 for your y values. If we plotted these points on the graph, we would have 0, 0, 1, 1, 2, 2, 3, 3, 3.5, 3.5, and so on. So that time will just keep going up from there. If we look at our next one, it says Christoph rents a kiosk in the mall to open an umbrella stand. He pays $6 to the mall owner for each umbrella he sells. The amount Christoph pays is given by f of x is equal to 6x, where x is the number of umbrellas sold. Graph the function and give its domain and range. So the type of function this is, it's per umbrella. You can't buy part of an umbrella, so it's a discrete function. So if we have the function f of x is equal to 6x, we're going to find values for x and y. We're going to use parts of 0, 1, 2, 3, and 4. So we're going to have 6 times 0, 6 times 1, 6 times 2, 6 times 3, and 6 times 4. 6 times 0 is 0, 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18, 6 times 4 is 24. So if we look here, our domain is the set of real numbers 0, 1, 2, 3, 4, and so on. Our range is the set of numbers 0, 6, 12, 18, 24, and so on. If we go to graph this, we're going to have 0, 0, 1, 6, 2, 12, and then it will go up. It will continue to go up, but we aren't going to draw that line because you cannot buy part of an umbrella. If you could buy part of an umbrella, then this would be a continuous graph, and then you'd be able to draw that line through it.